All right, so today I will be presenting one of the studies that I did as part of my PhD. So this particular one we carried out in Australia, so at Macquarie University with Australian students. And in this one, I studied like in the wider topic of my PhD, I looked at the cognition of programming, and this one in particular, it's about the cognitive skills that predict programming performance in this university course. So as an introduction, we here, of course, all agree that programming is an increasingly important subject that a lot of people are required to learn, but that is also a relatively new skill of which we still have a lot to learn about. What it is exactly, how it works, which other skills are related to it. And of course, there's a lot of speculation about which cognitive skills relate to programming and maybe predict how good people can be at programming. And one that or domain of skills that is often mentioned and has already been mentioned today as well, are these mathematical skills or algorithmic thinking skills. While at the same time, there's also a lot of discussion about whether language related skills relate to programming, because of course, to program, there's also a lot of learning a specific programming language with its specific syntax and vocabulary in a way that might be related to language skills. So these are also a bit the two domains that we started thinking about when setting up this study. So the aim of the study here is to determine the cognitive skills involved in computer programming, with specifically the research question, which skills predict programming performance following an introductory computing course. So people learning programming very early on as beginners. And to set out, to select the cognitive skills that we wanted to measure, we started looking at models of the programming process to sort of decide which skills we thought might be most relevant to start testing in this experiment. So this, I think, is a little similar as well to the models in the previous presentation, but the PGK hierarchy model divides the programming process up in 4 stages and 4 levels, starting with the problem level, and then the object level, then the program level, and the execution level. And to clarify further the aims of each level, at the program level, the programmer tries to clarify the problem that they are trying to solve with whichever programming endeavor they are going to do. And they try to find a solution for this program level, for this problem. Then at the object level, they try to translate this high level solution into a more specific algorithm. And then at the program level, they implement the algorithm in a specific programming language. So really writing it down in the specific language. And in the final stage of the execution level, the computer executes the code. So then we thought about the cognitive skills that might relate to each of these levels. And we thought that the first 2 stages, so the problem level and the object level, would be most related to algorithmic thinking and mathematical skills, where it's really about problem solving and translating that into algorithms. So really that algorithmic thinking. While the 3rd level might be more language related, because that is where the specific programming language comes into play. So people there need to learn and know the specific syntax and the rules of the programming language that they want to use, and perhaps also the limitations of the programming language that they want to use to really implement the program. And then at the execution level, there are not really any related cognitive skills, because this, of course, is done by the computer, so the programmer themselves isn't very involved. Then we looked at the specific really more specific cognitive skills that we wanted to measure for each of these domains. And we did this by looking at, for example, aptitude tests that IBM uses to select people who might be good at programming. We also talked to programming teachers in our university and read a lot of previous literature about which cognitive skills have been found in the past to be related, and we settled on the following 5. So in the domain of algorithmic thinking and mathematics, we thought of algebra skills, logical reasoning skills, and pattern recognition skills, that those might be important. And in the language domain, we focused on language learning skills, so the ability to learn grammar and the ability to learn vocabulary. So based on this model, we came to the following hypotheses. So first, we expected, of course, the way that we selected them, that all 5 of these cognitive skills would predict programming performance at the end of the introductory programming course. We also thought that these cognitive skills would cluster as we selected them. So with pattern recognition, algebra, and logical reasoning as mathematical algorithmic thinking skills, and the language skills, grammar learning and vocabulary learning as language learning skills. And from that, we then thought that both of these clusters, so both the mathematical and the language skills, would predict programming performance at the end of the course. Now, to test this, of course, we selected specific tests for each of these 5 cognitive skills that we would administer to our student population. And I'll just show you a little bit of examples for what the tests look like. So for the algebra test, the items look like this. So students were presented with a word problem, as you have probably seen a lot in your mathematics classes in high school and primary school. And from that word problem, they were then asked to select the correct equation that could solve this word problem. Then for logical reasoning, we presented them with these kinds of statements. So they get 2 statements that are given as true, the first 2, and then they have to evaluate whether the 3rd statement follows with certainty from the first 2 statements. So whether that is a conclusion, a correct conclusion that you can draw with certainty. For pattern recognition, we presented these number sequence patterns. So they have to to figure out what the next number in the sequence would be. So try to figure out the pattern in the number sequence here on the left, and then select the correct next number in the sequence. For vocabulary learning, we presented pictures of these kinds of all sorts of different creatures with their names, and they had to memorize the names of the creatures. For grammar learning, we gave them a task where they were presented with pictures with corresponding sentences in an artificial language, which has grammar rules. And from the picture sentence combinations, they can deduce the grammar rules, and then had to, for the question items, select the correct grammatical sentence for that goes with a picture. So these were the 5 tests that we presented, and we presented all of our tests digitally through Qualtrics. As outcome measures, we of course wanted to measure programming performance at the end of their course. So we used 2 measures for that. The first one was the SES1, which we had created and validated 2 short versions of. This is a test that was developed in 2016 by Parker et al. And covers, as you can see here, a wide variety of programming related topics. It consists of 13 questions. It has, which is quite a lot that they have to try and answer as many as possible in 30 minutes. And it's quite a challenging test with these kinds of items. Just as an example. So for example, in this one, they have to evaluate what the outcome of this function is if you put this input in it. And they're all multiple choice questions. So this test was not related to their course in any way. They hadn't practiced it. It's really meant to be an independent programming test, not related to their course. And then the second outcome measure that we had were their course grades. So this obviously is very course related. It's the grades that they got on their tests that they had to do throughout the programming course, also with a variety of topics. This had a more free format where they could use multiple attempts, and they had a bit more time. We're also allowed to use outside resources, for example, calculators and looking things up. So then for the study design, as I said, we conducted this in Australia, so with English-speaking students. In the first week of their course, in their tutorial, they completed testing session 1, in which they completed some demographic questionnaires, and then also all 5 of the cognitive tests there. Then they followed their 12-week course as usual, with no interference from us. So it really was an introduction to programming course, university-wide, with students from all sorts of backgrounds, but still predominantly more the science backgrounds and the computer science backgrounds, but also some students from very different parts of the university. And the programming language for the course was processing, which is Java-based language to learn. And then in the post-test measures, in the last week of their tutorials, again within the tutorials under supervision of their tutor, they completed our independent programming test, so the SES1 short. They answered some questions about also their level of English and whether they had seriously attempted the tests that we had given them. And then 2 weeks later, we got their final grades for the course. So the course grades that we also use as an outcome measure. Then looking at the data, we got 344 consenting students who completed both sessions. After excluding students who self-reported a poor level of English, which of course would be difficult because all our tests were in English, so we excluded them. And who reported that they didn't seriously try or do a serious attempt at the tests, we still had 282 participants remaining. Of those, there were 49 female, 204 male, and 29 who didn't specify. And the average age was around 19 years old. So then, of course, we set out to answer the questions that we posed at the start. So which cognitive skills predict programming performance at the end of the course? So for this, we ran a regression analysis with all 5 of the cognitive skills included, and also controlling for whether they had had any previous programming experience prior to their course. So that was entered as a control variable. So I'll walk you through each of the cognitive skills. So as you can see, for pattern recognition, we did not find it to be predictive for neither of the programming outcomes. So it did not predict the performance on the independent programming tests, and it didn't predict performance on the course grades. Algebra, however, did predict performance on the independent programming tests, so on the SES1, but it did not predict performance in the course grades. Logical reasoning predicted both, so it was predictive of the independent programming performance and of performance on the course. Grammar learning, again, predicted neither of the two. And vocabulary learning predicted performance only on the independent test, not on the course grades. So in summary, when you see them all together like that, we find that pattern recognition and grammar learning, against our expectations, did not predict performance either way. Algebra and vocabulary learning seem to predict it, but only on one of our tests, and logical reasoning is the most consistent predictor, predicting it on both of our programming outcome measures. Then the second question was, do the cognitive skills cluster in a mathematical and a language component? And for this, we used structural equation modeling. And we saw that indeed a model with the tests clustered, so as we hypothesized at the start, into a mathematical component and a language component better explained the data than one where we just have a cognitive skills component. So once we had that, we wanted to see, of course, do both of these clusters then predict programming performance, or is one more predictive? So this is the model with programming defined as the independent programming test. And we see that algorithmic thinking and mathematical skills as a component containing these 3 tests is a significant predictor of programming performance on this test. But language skills, however, are not predictive of programming performance. And we see very much the same pattern when we look at the course grades. Again, algorithmic thinking and mathematical skills as a component predict programming performance, but language skills do not. And in both of the cases, we do also see, of course, that these skills are also to an extent intercorrelated. So in summary, we find that logical reasoning seems to be the most consistent predictor. Algebra and vocabulary learning do predict performance on the independent programming test, but not on the course exams. We see that mathematical and algorithmic thinking skills predict programming performance on both outcome measures, while language skills do not. And some of these findings, of course, are against what we expected from the start. So we had a little bit of discussion about why that might be. So first interesting finding is that there seems to be differences between how skills predict performance depending on whether it's our independent programming test or the course-related performance. So generalized versus course-related programming performance seems to be predicted differently. And we think that the main reason for this might be the format of the tests. So particularly when we look at the SCS1, so the independent programming test, we see that it used quite a strict format. So there was a lot of time pressure, and there was no calculators allowed, no use of outside resources allowed. And when we look at the skills that predict that test, but don't predict our course-related programming performance, we see that that's vocabulary learning and algebra, which might be more relevant as skills in performance on a test when there is time pressure. So you have to work quickly and have those algebra skills, for example, very active. Also no use of calculator, of course, so maybe a bit more reliance on algebra skills because of that. And perhaps also more emphasis on memory, which is very important in our vocabulary learning test, of course, because they were not allowed to use these outside resources and had to maybe memorize the programming language quite quickly to be able to evaluate that test. Whilst on our course-related programming performance, they had a lot more freedom. So maybe those skills were less important there. Then the second surprising finding is the lack of predictive ability for pattern recognition. This previous studies a little bit longer ago, mostly in the 80s and 90s, did find some pattern recognition effect. One of the explanations why we might not have found that is that in previous studies, they sometimes split programming skills into different domains. And pattern recognition seemed to be most predictive of syntax ability of programming, which is something that we didn't test explicitly in either of our programming measures. So we never really tested people on their explicit knowledge of syntax, like have you memorized that very well? Perhaps if we had, maybe then we would have found pattern recognition to be predictive. Another difference might be the requirement for code efficiency. So in our tests, one of them was multiple choice, so they didn't have to make their own code. And the course-related tests really allowed quite extensive code. As long as it worked, it was okay. And perhaps pattern recognition might be more predictive and important when there are rules for how efficient your code has to be, so that people have to make more use of structures such as loops and these kinds of statements. I can't click because someone wanted to enter. And then lastly, the type of pattern varies across tests. And it seems like some of the tests that tested visual pattern recognition were more predictive, while ours, of course, was a number sequence. So there might be a difference in that, but we don't fully understand why that might be. And then lastly, a surprising finding, of course, is the lack of predictive ability for language skills, for which we have had a few possible explanations that will need to be tested further in the future. So first, it is different from another study that was published recently by Pratt et al., who did find language skills to be relevant. However, their language skills were also more memory, had a large memory component. And we see in our tests that also the test that had the largest memory component, the vocabulary learning test, still showed some predictive ability for our independent programming test, while the language skills, as measured with the grammar learning test, where the examples stay available, so it's not really memory based, did not predict. So there might be importance of memory in language skills rather than just broader language skills. Secondly, there might be it might be a result of the way that we teach programming skills and also the way that we tested it in our tests. So as I said, we didn't very explicitly teach programming syntax, and we also didn't very explicitly test that. And that seems to be a pattern in modern programming education generally. So it might be that just generally as in education, and especially in our course as well, where we did this experiment, we focus more on the problem level and the object level of the programming process and a lot less on the program level. Hence, algorithmic thinking and mathematics perhaps plays a larger role in predicting ability in those kinds of courses than it would maybe in a course where the program level is also very explicitly addressed. And then finally, it's also, of course, possible that natural language, so human languages, are just too distant from programming languages and therefore don't predict. But then future studies would be necessary to investigate that further. So in conclusion, based on this, we would conclude that logical reasoning seems to be the most reliable predictor in our course with this programming language as we have tested. Of course, future studies will need to show whether that's the case also with different programming languages in different kinds of courses. Algebra and vocabulary learning may predict as well. That mathematical and algorithmic thinking skills seem to be more predictive, at least in the current context. And we suggest that perhaps differences in teaching and testing methods may favor different cognitive skills. So cognitive skills may depend on the way that we teach and test in education. And the rest, all these suggestions, of course, will have to be studied further so that we can see how far they generalize. Then in acknowledgements, I would like to thank all these people and institutions who helped and allowed us to test and allowed us to use their tests. And then I still have room for questions and discussion, I think.
Thank you very much for this, again, really very clear and good to follow presentation of the research that you've been doing. In your discussion, you pretty much answered all my questions. I guess that's different for other people. So the floor is open for questions and discussions. Sally was the first. You want to ask your question?
Yes, thanks. Thanks for the talk, of course. I was wondering, so in the table where you have the 4 phases, you explicitly said that in the execution phase, you do not expect to basically to have any cognitive skills being present because it's just the machine executing the program. And I can understand that that reasoning, but I was wondering where in those phases does debugging come into place? Because obviously when you execute the program, you realize, oh, actually it didn't work. And so then you go back, and that the going back and adapting the program, whatever you made, obviously would take some cognitive skills. So I was wondering whether you thought about what skills those would be and how they could be included in your basically the future research, right? Because you did this already. Because I think both in the course outcome, they did have to focus on making sure that the program actually worked. And then also, I guess, in the multiple choice, you still, I know for myself that I would think this is the answer and the answer is not there. So then I would also have to go back and, do sort of the debugging, I guess.
Yeah.
Is my answer, like my question, clear?
Yeah, I think it's a very interesting question. And we did also discuss where in this model would debugging sort of fit in. It's not very explicitly in the model. It's also not very often very explicitly assessed in programming tests, but of course it is a big part of it. I think it would be too simplistic to put it at the end in the fourth stage, so the computer execution stage, because I think where it falls would really depend on the kind of bug that you get. So the kind of where the error sits will, I guess, define at what level you have to work out the solution to the bug problem. But of course, then there remains a stage where you have to figure that out in the first place, right? So at what level is the problem? And I'm not entirely sure where you would place that, or if perhaps it would have to be a different level, or if you could perhaps say that again then is the problem solving level, where you try to figure out define the problem that the bug is indicating, and then select the level. So perhaps it's a programming language level, perhaps it's an algorithmic level to which you move then. So perhaps it moves, debugging, I think, might move across the model depending on the bug. That I think would be my speculative answer to this question. But yeah, very interesting.
Okay, thank you. Joseph?
Thank you for the presentation. I wondered how much variance can you explain with your model, and do you also include context variables like gender, because you have data on gender? Thank you.
So we didn't include. I looked a little bit exploratively at the effects of the demographics, but in the end, the only demographic that we included in the model to control for was the previous experience in programming, because of course in our study we didn't test programming performance at the start. That was mainly, we did try to do that in a pilot, but the test was just way too difficult for people before they learn any programming. So it was very stressful and disheartening for them, and they were generally just at the floor anyway. So we only test performance at the end of the course, and of course that is probably largely their performance because of the course, but could also have been due to some previous experience. So for that reason, we included that in the model, but not the other demographic factors. As for the variance, I don't know that off the top of my head, how much that explained, but I do have the full tables as well somewhere to show.
Okay, so maybe that can be checked later. Sure. Ferenc has a question as well.
Yes, thank you. So thanks very much for the presentation. It was really interesting to hear about these results, and I was especially intrigued about the results on language. And basically, in the end, there was no prediction, no contribution of language to programming, and your argument was that maybe natural languages are too far away from programming languages. Here I really wonder whether, so would we want to say that natural languages or skills in natural languages are not associated with programming, or we would rather say that certain aspects of language may be, but that might be related to linguistic skills? Now I would like to refer back to the keynote before, referring to Latin, which is a very pragmatic and grammatic language. And yeah, obviously it's rather different from German, rather different from English. So would you see a continuum of languages and certain linguistic skills or certain linguistic peculiarities that might be relevant in terms of programming, or is it just rather no?
Well, yeah, when I set out to do this experiment, I really thought language skills, especially, certain parts of language skills would be related. And honestly, I still think that there's a very good case to make for language skills being related, but we didn't find it with the language skills that we tested here, and also with the programming outcome measures that we used here. So I think that it's very well possible also, because the language test that for grammar that we selected it's not Latin, of course, because we wanted a completely like a language that no one has seen before. So it's completely artificial language, but it's very much the same sort of idea with a very, very clear grammar rules and no exceptions. And these, you know, so we thought that would be very closely related to a programming language, which is also a language with really no ambiguity, because otherwise it doesn't work. But we don't find that. And like I can't tell, obviously, based on the current study why that is. But personally, I think it is perhaps more related to the way that we test the programming knowledge at the end than due to the fact that the skill is too distant, or that the language is too distant from programming languages. I think that perhaps if part of the programming test was, without checking anything, write a correct sentence of code in a, or select a correct, grammatically correct in the programming language sentence of code, that then perhaps you would see predictive ability for this kind of syntax learning in natural languages. But the reality is that we don't really, or didn't really do that in either of our tests. They are not required to really know off the top of their head the entire syntax rules of the programming language. They can always check that or look it up. Does that sort of answer the speculation?
Yes, absolutely. Thank you. So, yeah, I really see the point that, and yeah, we've got the same problem in how exactly programming could be measured and what would be the best way to do it. And yeah, I see your point that in this case, maybe the measure itself might be responsible for the lack of association.
Yeah, and we can't tell unless we do the experiment or a similar experiment with different measures, obviously. So yeah.
Okay. Just want to point your attention to a comment by Engin Bombacher in the chat, who pointed out a study to us, which perhaps we should check in that respect. Yeah. And if I understand it correctly, the conclusion of that study, or one of the conclusions perhaps, is that understanding computer code seems to be its own thing. It's not the same as language, and it's not the same as math and logic. So, yeah.
Very interesting.
Okay, thank you.
Sorry, I just want to add quickly some thoughts on that. It's like they're also distinguishing between the learning process and the, like, once you have learned it, what parts of the brain are actually involved in reading code, and that's a distinction too. But it's a small, it's like a small interesting study. But
I have seen the study as well before, and indeed I think there's a difference in that you see also in their proficient programmers versus the people who are still learning. So there's definitely, I think it has been a while since I looked at it, but I think it looked more similar to normal language in people who are more proficient. So it might be that it becomes more like a natural language if people know the programming language really well, which I guess would make sense. But it definitely a very interesting study.
Yeah.
Okay, Wolfgang has a question as well, please.
Well, I came late to the talk, sorry, because I had the chair in the other, but I just remembered that I recently followed this wonderful demo from OpenAI about CodeX. And this is really interesting because the GPT-3 system learned not only human languages and translating by itself by being exposed to examples, but just without any plan, it also learned to program. So this is a general system, and it learned languages, it learned translations, and it learned programming. And now it's a product that was bought, I think, from Microsoft and is used in GitHub as a coding buddy. And I saw the demo and it was mind-blowing because it's exactly the kind of computer games that kids create every day with our tools, which were done there by just entering natural language, and the system translated it into code. Amazing, mind-blowing, but this could also have some implications of the general principles behind coding and human languages. just a remark, but this is a recent thing, but really fascinating.
So I think this needs some more research. We just had a comment from Josef Gugemos, who says they also had a study where language skills did not predict mathematical and reasoning skills. So I think we have to do more research on this. That's pretty obvious. That's exactly why we are interacting.